we've got good news because we're having a good discussion, because that means that we are pushing against time a little bit. And our speakers unfortunately have to leave you, at least not Prague, but leave you around 1 o'clock because there are some administrative procedures for them to sign. So we're going to squeeze Jimmy into the time frame, and we're going to continue general discussion. As you know, there'll be another talk at 5 o'clock this afternoon, to which you are more than welcome, and we can take also some questions about this morning. Okay, so that we stretch it into the afternoon because we are pushed by the administrative necessities, unfortunately. So if you could bear that in mind. So let me just say a few words. Jimmy Melskens is well known for his work. Well, I think initially and probably still now in amorphous silicon, I think, but he's going to tell us something a little bit broader, I believe,
yes,
than just amorphous silicon. Some very exciting words. Jimmy.
All right. Thank you, Tom, for the nice introduction and also invitation to the event. It took quite a while for me to get here, like 2.5 years of postponing, and I'm very happy that we have the meeting live in person and not online, because I think this is a lot nicer. So thanks for organizing once again. So my background is in electrical engineering. Indeed, I used to work in Delft, first as a student, and then I did my PhD also there on the amorphous silicon defects. Then I went to Eindhoven University, which is the building you see on the left here on the screen. And I spent some time there working on the surface passivation in crystalline silicon PV. So no longer amorphous silicon, although, as you will see in the talk, amorphous silicon is part of crystalline silicon wafer production as well, cell production, I mean. And I recently, since the beginning of this year, I moved from academia to industry. So now I'm working in this yellow building that you see on the right-hand side over here, which is a company called HyET Solar. In the past, it used to be called Heliantos. It's also known to people here, I think, in the audience to some extent, and they make flexible thin film silicon modules. So again, based on amorphous silicon. So for me, it's kind of a closed loop back to the topic where I started. And what I will do today, my plan originally was 3 years ago to talk about the oxide passivation on crystalline silicon, but because this I changed in my jobs, I'm also going to tell you a little bit about what I do now in Arnhem at HyET. So let's talk first about the outline. I'll tell you a little bit about nanolayers in crystalline silicon PV, especially surface passivation, what this is and why it is even important. Then I will tell you about passivating materials, also why they are important and what we can learn from them. I'll give you a couple of examples of these surface passivation mechanisms. And then we'll talk at the end of the talk about the nanolayers in thin film silicon PV. So which layers do you need in those devices, and what is the industrial potential of this flexible technology? All right, let's go then. So first, a brief history here. Of course, PV research has been going for a long time. Amorphous silicon that you can see here at the bottom of the screen. It was already investigated in the 1960s and 70s as an absorber layer material. And then a bit later on, people also discovered that you can place it on top of crystalline silicon to passivate defects that you have there. So that line that you see on the left-hand side are, let's say, passivating materials that are, supposedly, are classical materials. You find them still in today's crystalline silicon cells that you find everywhere nowadays on rooftops. And in recent years, actually, there's been quite a revival in this topic, and now people are exploring all kinds of different materials. Let's say more exotic oxides that you see on this timeline over here. And I will talk a little bit more about this topic today. So many of these materials are just passivating materials, which basically means that they're able to passivate electrical defects at the surface, and this is their sole function. It's also possible that you have these materials that they are also acting as a contact material. So that means they're conductive to either electrons or the holes. These materials we call passivating contact materials. And many of these are actually made by atomic layer deposition, which is a technique that is very suited to make really thin materials of a few nanometers thick. And it's a popular technique also in industry nowadays. So let's zoom in a little bit more. Surface passivation, I already mentioned it. So what is it now really? So what you see here is a very basic diagram of a crystalline silicon cell. You see on the back side, you see a slab of aluminum over here. Then you see some, let's say, reddish zone over here, which is the so-called back surface field. The aluminum acts as a dopant when it diffuses into the silicon. And on the front side, we have some emitter, and then silicon nitride usually, and contacts in between. So what we want is basically when you absorb your light, you make electron hole pairs in your silicon. You want to get the carriers that you generate towards your surface, and then you want to collect them to have your current actually at the external terminals of your device. So in order to achieve this, we need to make sure that we don't actually lose those generated carriers once they reach the surface, because you want them to get over here and over here. And basically all these other areas in between are potentially regions where you can lose them. And this mechanism is known as surface recombination. So we don't want that. And we have these non-contacted regions. And to mitigate these recombination losses, we use passivation layers. Usually these are dielectric materials that are not conductive themselves. Then we also have contacts, and you want to selectively extract your holes or your electrons, and then you get your passivating contacts, as I mentioned earlier. So now we look at one example for p-type surfaces in crystalline silicon, aluminum oxide. This is probably the most common material nowadays to passivate p-type surfaces. So how does this work actually? You have some defects that are present in the bandgap of your crystalline silicon over here, as characterized by these lines. So you want to reduce that density, and the way to do this is to basically bring new elements there. So there's also the aluminum oxide and also hydrogen, which is in this material. And in this way, you can reduce this so-called DIT, or the interface defect density. And this is the chemical passivation. What you can also do, and that's happening in the case of aluminum oxide, that it creates actually quite a large negative fixed charge near the interface, meaning that your electrons are repelled, and the holes can just accumulate there. So that means that the minority carriers are basically repelled, and that means that you don't have both carrier types present at your surface, meaning that the chance of recombination is just reduced. So this QF parameter is important to increase it, so you repel your minority carriers. So general guideline is that we want for p-type silicon to have a negative QF, for instance aluminum oxide, and for n-type surfaces people use silicon nitride to get this positive QF realized on the silicon. Now then, so how popular is this now? So here we have the ITRPV roadmap. It shows different types of technologies, so it's a little bit small, but you see that the bulk of the materials here is the, the picture I showed you before, this aluminum BSF cell. I mean, this is the basic solar cells losing popularity now in favor of the cells that you see in this orange block over here, which are the so-called PERC cells, or passivated emitter rear contact cells. So already here we make use of a passivating contact, you might say. The difference is that we don't have anymore this aluminum basically everywhere over here, but we have now small openings in this material. And in between, you see another material, and that's our passivating material. So you effectively improve your recombination on the rear side, or just reduce it by having this contact configuration. So these are now the most conventional cells that you find in all kinds of modules that you can get for your rooftop. Efficiency is already, let's say, approximately 23% there. So the trend is that we go from this bottom structure to the board towards the PERC cell, which is to a large extent actually enabled by aluminum oxide, which we have also over here on the rear side in combination with silicon nitride. Then some more details here about methods, actually, how you make this aluminum oxide. So in the past, people used to use chemical vapor deposition to make this layer. Nowadays, more and more companies are moving towards towards ALD, atomic layer deposition, because it's known to be actually providing a bit better preservation, and also the uptime of the machinery is higher. So lots of companies are now considering this change, meaning that the market share of ALD, aluminum oxide, is increasing. Then actually, is it possible to progress still beyond this point? So of course you want to increase your efficiencies more and more. Well, the answer to this question is yes. So then you need to look for ways to reduce your recombination losses even more. So that is done by looking at new passivation materials, and also shifting from this conventional structure approach with your contacts towards more passivating contacts. Because over here you basically still have metal in contact with your silicon, and that's not exactly what you want. You would like to have a full contact that is also passivating, and that is what you see on the right-hand side over here, which is nowadays known as the TOPCon structure. Was first pioneered by Fraunhofer in Germany, but the structure actually is not that new. So they make use of technology already from the 1980s, which is a combination of doped polysilicon with a very thin silicon oxide layer in between. And then this silicon oxide is basically acting as a chemical passivation layer, and the doping your polysilicon is the field effect, in basic terms at least. So even if you do it like this, then your efficiency can already exceed 25%, and there's even companies now in China already making these kind of modules. Yeah, I have one example shown over here. So now then, what are these passivating contact cells actually looking like? So we want to have basically full area coverage of your wafer. And then you see that actually everywhere in this whole design, it's all about making very thin films. So you start with a very high quality wafer that you just buy, and then you texture it. And everything else almost is a thin film layer, thin film fabrication. So the TOPCon cell we already discussed on the previous slide, you see on the left here. Another structure that's also quite classical already since the 1990s is the so-called heterojunction cell, which is based on amorphous silicon. So here we first have an intermediate layer of intrinsic amorphous silicon, which is providing chemical preservation, and then doped amorphous silicon on top of that to provide carrier selectivity. So you might say that both of these are actually heterojunction devices. One of them is based on CVD of amorphous silicon, whereas the other one is a more high temperature process route. So yeah, there's this whole field now booming basically on metal oxide passivation. I will not take the time to go over everything, but there's many activities in this topic. So there's different electron selective contact materials, hole selective. There's also tunnel oxide based contact structures. And in this context, you also want to have high mobility TCOs, because you will need them on either side of your cell to conduct your carriers laterally. And there's many activities also on this topic. If you're curious what it means for the roadmaps, we can look at this picture, which I think is very illustrative. So you see this aluminum BSF cell was basically leveling out over here in efficiency. Then industry said, okay, let's go for the PERC cell. And then you go here. And nowadays people already need to move towards passivating contacts over here. The next step will be silicon-based tandems, meaning you put your perovskite cell on top of your silicon, then the perovskite cell is actually acting as an add-on to the already existing crystalline silicon PV technology. So to keep this going, you need to go in that direction, according to many people. Then some more reading here on the materials for passivating contacts. A paper I wrote myself on the left-hand side, which was covering the first principles and new materials, and then some more industrial approaches already outlined in these two more recent papers, with even more new materials being investigated by new people. Okay, so then we already saw that we have quite some material options. So what is now actually interesting and what is important? So if you break it down again into interface defect density and fixed charge density, you see that there's quite some materials which have been investigated. See all kinds of data points from different literature here. So you see in terms of DIT, I would like to be low. So you see here amorphous silicon in the middle showing really nice low values. That is the reason why the heterojunction cell is so successful. You see also other materials with low values. Then on the right-hand side, we see the fixed charge density. You see a group of, let's say, very positive values, which are good for n-type materials, and very negative values for the p-type materials. So there's quite a variety, and the question is, what is now the best for which type of architecture? And is it possible to combine both a low DIT and a high QF together? So that is the introduction to the materials that I want to discuss today. So we have recently investigated a stack of phosphorus oxide with aluminum oxide, and also doped zinc oxide, which both have actually quite interesting characteristics, and I will talk about them a bit more from now on. So this first one then, it is interesting to look at this because it might replace silicon nitride or maybe enhance the passivation provided by silicon nitride. So let's look at this. Why is this interesting? So you have already in existing PERC cells, you have M+ regions. On the front side, we have this emitter over here. So you would like to passivate this with a good layer. Nowadays, people do this with silicon nitride, which is also anti-reflection coating for your cell. But is it maybe possible to improve this by inserting another layer in between? There's that light green layer over there. It could be this one. So if this layer is firing stable, because you make these contacts by firing through, it might be interesting to add this. So this layer stack sounds quite exotic. It's not really a classical material for PV purposes, and people have not looked at it for a very long time. It was originally developed by a colleague of mine from Eindhoven, and he looked at this material for a different kind of technology, for nanowires, for 3.5 applications. And then, of course, nanowires are a 3D surface, so you need some technique that can actually formally code this difficult surface morphology, meaning the route was chosen for ALD, and they developed a recipe. So it was possible to grow this at different temperatures, and it was growing quite all right. It was also established that phosphorus oxide is really hygroscopic, so if you don't cap it with another material, it reacts in air immediately after you take it out from your deposition tool, and that's not what you want. So the capping layer chosen was aluminum oxide, just because it's very easy to make it with ALD, and it is a known process. So this stack was born like this. And then the question was, is it possible to actually passivate crystalline silicon with this stack? So the recipe details are over here. So you have basically cycles. In atomic layer deposition, you don't bring all your precursor or reactants together, but you do it in a sequence. And we use these precursors over here. So TMP over here and TMA for the aluminum oxide. The initially developed process was not self-limiting, meaning that the growth still keeps on going basically when you inject more precursors. So in that sense, there's not a pure LD process, which already raised the question, is it not better to go for a CVD-like process where you purposely actually put all the reactants together anyway, because then the growth can also be maybe quicker, and it is easier to make it with other kinds of industrial equipment, which is also familiar with CVD. So we went for that route. And then we look at test structures. So typically for passivation studies, people like to look at symmetric cases. So you have your crystalline silicon wafer, then your passivating stack on both sides, and you try to understand actually how well this is passivating. The working mechanism, of course, is interesting, and you want to compare it to other kinds of passivation materials. So you see here already a picture from the microscope where we indeed managed to make these layers as closed layers, even with very low thicknesses. So everything is nice and conformal on your crystalline silicon surface. The passivation quality then for the ALD recipe was tested for different temperatures, and you see here on the horizontal axis annealing temperature, which is what you need to do to activate your passivation quality. You, for instance, make it possible for the hydrogen to move actually from your passivating layer towards the silicon interface, and then your lifetime, as we've seen in the previous presentation also, that's a very important parameter for passivation quality as well, although now the time scales are much longer. We talk about milliseconds or more. So with this ALD-like recipe, it was possible already to exceed 1 millisecond, which is quite a good value. And then also with the CVD-like recipes, we got very low J0 values, which is the a recombination parameter, also linked to passivation, and you want to reach really low values for this. Then, is it possible to understand how this actually works? So then, if we express it again in terms of this interface defect density and fixed charge density, and we grow our stack at different temperatures, you see interesting trends. So for lower deposition temperatures, you see that my surface passivation is improving. You see this trend over here. So your DIT is really reducing by orders of magnitude if you do this. And if you anneal, as you can see over here, you see also that your passivation quality, now expressed in effective surface recombination velocity, is also improving. So by both using the growth temperature and annealing temperature, you can manipulate it. And the good thing is that we have this high positive fixed charge density already immediately. So if you grow your layer stack, we have this high value. And if you do different things to your growth, it's not really manipulating much this fixed charge density. So that's a good thing. And it already makes it promising in that sense. If you can manage to get also low DIT values, then you probably have a good material for passivation. If we then try to understand a little bit more the layer composition with SIMS, we see that aluminum is actually mixing into my phosphorus oxide layer already in the as deposited state, as you can see here. If you go for some annealing, as we've done here, we see that the distributions actually mix a little bit. So you redistribute your aluminum, phosphorus, and your oxygen. Structural changes must be there. And also hydrogen, which you cannot detect so easily in this way, although you see also differences there. It must also reach this silicon interface. So we hope that we passivate our surface with dangling bonds in this way. If we then investigate a bit more detail what the structural changes look like, we use FTIR spectroscopy, also a very popular technique to look at thin films. And in this way, we see that certain bonds are much more pronounced after you anneal, while others disappear. What's especially interesting is that you form aluminum phosphate, this AlPO4, and it might be beneficial for surface passivation, while you also release hydrogen towards your silicon interface. Then effusion measurements, they're also popular in all kinds of thin film investigations, and this is where we see that hydrogen indeed becomes mobile. So here you stick your thin film in a vacuum tube, you just gradually heat your sample and measure the hydrogen that's coming out. You're just counting it as a function of temperature. You see that, hydrogen is moving because we see has increase over here, and also this so-called effusion spectra are different, meaning that the bonding configurations in your passivation stack are not the same for these growth temperatures. This also supports the fact that we believe that we have hydrogen reaching the silicon interface, meaning you can passivate your dangling bonds there. Yes, so passivation by hydrogen, and you form your aluminum phosphate. Now, actually, what would this look like in devices? As I already said, you can insert this stack maybe here on the front side of your PERC cell. And we did not get to the point that we really tested this in real devices, but we got quite close. So we first wanted to establish whether you can passivate heavily doped surfaces, this N+ region that you find in PERC cells. And then you see if you have different kinds of doping levels as expressed by the R-sheet value that you see over here. We have a lowly doped surface and a more heavily doped surface. In both cases, you can end up with quite low J0 values, meaning that it is interesting indeed to use on the N+ surfaces. And what do these values now really mean? Because it's a bit hard to just guess it like this. If you look at different values here, these are basically state-of-the-art passivation schemes for N+ silicon. And we see stacks of, for instance, silicon oxide, silicon nitride, and silicon oxide, this O and O stack, as they call it. This is basically the best scheme that you can have at the moment. And our data points are basically in the same range. So this means that we are at least on par with the already existing passivation schemes. So conclusions. for this topic at least, we have seen that this phosphorus oxide aluminum oxide stack can achieve excellent chemical preservation and also field effect preservation. Annealing improves DIT. Also, deposition temperature can be used to lower the DIT. Your high QF value is already present after your deposition, so you don't need to worry too much about optimizing this. And chemical preservation is understood to be linked to the formation of AlPO4 and also hydrogen, which is released. And then it is indeed possible to passivate typical N+ silicon surfaces that appear in conventional PERC cells. So that is part one of my material overview. And now, of course, this is not a contact stack, really. So it would also be nice to look at passivating materials that can also conduct current. And then a choice that I was made here, I actually doped a zinc oxide. A doped zinc oxide is a transparent conductive oxide, so we know that it is already conductive. It's used as a TCO in many kinds of thin film devices. And one of my ex-colleagues, Bas van der Loo, here in this paper demonstrated when we tried to put this on crystallized silicon, also an ALD process for the zinc oxide, that it actually gave very good passivation. So now the passivation quality is expressed in terms of the implied VOC. We see here that for different tunnel oxides, there are different values. So if you just HF dip your wafer and then you grow your zinc oxide, you don't get really a high value. But if you take care that you control this interfacial oxide well, so you can use, for instance, nitric acid oxidation of your surface or a typical RCA clean or UV ozone cleaning, and then you grow your zinc oxide on top of this, you all get quite nice values. So that's the first ingredient. We need to make sure that the interface is well controlled before you grow your zinc oxide on silicon. So what else do we need then? We need some heat. So also, like in the previous case, you need to anneal your sample to make sure that hydrogen is probably able to move and reach your silicon interface. So here, for different kinds of interfacial oxides, don't worry too much about all the data points, but you see that if you increase the annealing temperature, you eventually improve this implied VOC, meaning you can reach high values. Then, what's also important is that we cap our layer. So, as we saw for the phosphorus oxide, that is actually hygroscopic, and then everything goes wrong if you don't cap your layer. A zinc oxide is not so much hygroscopic, although it can also react with water in the air. But the issue is more, I think, that we have crystalline grains. So a zinc oxide is just a crystalline material, and the hydrogen, if you start to increase your annealing temperature, can escape along the grain boundaries towards your top surface, and then you lose your hydrogen at the silicon interface. So what was done here was again to use this already well-known aluminum oxide process and stick it on top of our zinc oxide. And then we see in this Sims picture over here that if you do forming gas annealing, this FGA over here, if you have no aluminum oxide capping layer, you lose a lot of hydrogen. If you put a capping layer on top, before and after annealing, it's kind of the same. So this really shows that the hydrogen is preserved in your zinc oxide. And also doping is important. So if you look at the measured minority carrier lifetime here, if you take some intrinsic material, which is in this case marked as hydrogen doped zinc oxide, because we always have hydrogen, but if you then also intentionally dope it with boron, you see that now we have a dopant in our material, meaning you can also benefit a little bit of the screening provided by your dopants, or the field effect passivation, if you like. And you see that now my lifetime is increasing actually as a function of the electron density or just the boron doping level. So these are the four ingredients that you need to make passivating zinc oxide with doping. So how do we actually make this? We use, again, an ALD process. In this case, it is a thermal process, so that means you dose your TMA, and then afterwards you dose water. For the zinc oxide, we use diethyl zinc as a precursor, and then you get a matrix that looks a little bit like this. So you have a zinc oxide matrix, and in between you have planes where you have aluminum. And this is the way you make doped materials with ALD typically. So then, is it also possible to combine this with already existing interesting architectures in crystalline silicon cells? So we saw before that polysilicon contacts or TOPCon-like structures are now very popular. Texture is what you need anyway to improve your light trapping in your devices. So basically always you have textured wafers. And here we looked at what the passivation of such samples. You see, if you have a textured wafer, your implied VOC is already quite nice and high. And if you take anti-polysilicon, as you would have in the top configuration, also in this case, you can reach really high implied VOC values. So this is actually quite promising because you can combine it with those already existing structures. And anti-polysilicon is a good contact, but it is also quite absorbing. So it would be nice if you can put a very transparent conductor on top of it. Yeah. So here again, the same picture. How good is then the passivation provided by our zinc oxide? We compare to other conventional materials that I discussed earlier, together with the phosphorus oxide. And now we see also here, for different kinds of doped surfaces, that we are over here and over here. So we are really in the same state-of-the-art regime, and you can use this basically on conventional N+ doped surfaces appearing in crystalline silicon cells nowadays. Then the contact resistivity, this also improves. So doping improves the contact resistivity. I typically want to have as low as possible contact resistivity to mitigate losses in cells. So here also on a different doping level, you see that the improvement is there, more heavily doped, and also on the N-type polysilicon case, the same argument holds. Then I'll try to understand these nanolayers a little bit better. So we use TEM actually to see what's going on. We have, in this case, at 400 degrees annealed, a sample that's very well passivating. We have textured silicon and a very thin interfacial silicon oxide layer. And then we get a zinc oxide over here, and then some silver over there. So what you see already from the growth process that I showed before, where you have your zinc oxide matrix and your aluminum planes in between, you can really see on the microscope that it is also there. So these aluminum dopant planes, they are over here. So that is nice actually, that it confirms that the growth is like that indeed. What happens if you go too high with your annealing temperature, then you lose your passivation. And if we then look again over the microscope, I will see different things. So you see that you form actually large columnar grains over here. So the mobility of the carriers in those grains is probably improved, but at the same time you can lose your hydrogen. And there's also rough interfaces now over here. So this is probably due to thermal stress and not good for passivation. Also, we form even voids in your material, which you can imagine is just bad for passivation because you don't cover the whole surface anymore with your material. And this is due to maybe hydrogen buildup or pressure in your material that you don't want. So is it then possible to make this using industrial tools? The answer is yes. So in Eindhoven, there's a few companies that have been busy with atomic layer deposition machines now for some years. And this company's Salt was so nice to try this process on their machines. So we compared basically the lab scale process that you see here as temporal ALD, that is the Eindhoven University result, and then we used a spatial ALD reactor, which is the green data set. We see basically that the results are more or less the same. If you want to be very picky in terms of lifetime, it is a little bit better even. So we might say that it is at least matching the results from the university labs. So if you go for more optimization, it can maybe even better. So conclusions then, passivation. It is possible to passivate textured N+ doped surfaces very well with doped zinc oxide. Also for polysilicon context, this works very well. We can reach really low contact resistivity values. And I didn't discuss it much, but also transparency and conductivity are really high. We are matching the, let's say, indium-like levels for instance, ITO or indium oxide, mostly due to the improved carrier mobility that happens during annealing. All right, and how does this then apply to solar cells? I think I already mentioned the PERC cell a bunch of times, so that is obvious. On the front side, for the rear side of the TOPCon cell, we might also use it, and more in the future we can combine with perovskites. You also need a tunnel recombination junction that is transparent, also doped, and it needs to be passivating. So over here, my blue layer, that is the zinc oxide. It can be used over here, and actually there's already running research in Eindhoven still now on this topic to combine the a crystalline silicon bottom cell based on the PERC approach as supplied by Q-cells, for instance, and they work together with the university to devise this structure and reach higher efficiencies. Okay, so that brings me to the conclusions for part one. I hope I've convinced you that you can make highly positive fixed charge density materials as an alternative to silicon nitride. And yes, it is also possible to expand beyond the functionality of just a passivating material by going to a passivating contact. Zinc oxide with doping is one example. There's many more passivating materials. I don't have time to go over all of them, but I think these are the two stacks that I'm most familiar with that I also think are very promising. And yeah, if you're curious, you can read more in literature about this. So then, for something quite different, but not so different, is that in the thin film silicon devices, we also make use of nanolayers, or very thin layers. And what does that actually mean? So I would like to tell you what I'm doing right now. So I switched the beginning of the year from the university or research environment to a company, HyET Solar in Arnhem, the east of the Netherlands. And they've been busy for about 5 years now, first at a very small research level, and now there's a real production line, and they want to upscale. So what does the company do? They make thin film silicon devices. I will tell you a little bit about the industrial potential and the progress in this technology. So what is thin film silicon in this context? I think for some people here this is very familiar, but I'll just briefly go over it. Basically, you have a substrate. In academia, people like to use glass, as you see here. And then you make a front TCO, zinc oxide with doping, for instance. Again, aluminum doped zinc oxide, as we saw also previously. Then we have different stacks of silicon. At the bare minimum is that you have PIN. So the I layer is the absorber. And then you have also a P layer and an N layer to serve as a carrier selective layer for the holes and electrons, respectively. What you can also do is put multiple junctions of these materials on top of each other with different band gaps. For instance, this example here, where we have amorphous silicon first, and then microcrystalline or nanocrystalline silicon as a bottom cell. Then we have a back contact, and then some back encapsulant. So this is the basic structure that many groups worked on in Europe. The topic has become a little bit defunct because there has been a huge competition with crystalline silicon PV. Of course, nowadays many modules are just made in China, and a lot of people are happy with it, but I will try to explain you today that it is not completely game over for thin film silicon. So stable efficiencies, they are quite low compared to crystalline silicon. As you see, for the single junction, we talk about 6 to 8%, and for the tandem, let's say, reaching up to 12%. Whereas for crystalline silicon, we can nowadays get 20, 21%. So you might say, what is the point of this? I will get to that. There's some unique selling points. So first of all, in thin film silicon, we use only abundant materials. And then it is possible to have only very limited performance losses due to heating. So this temperature coefficient that is apparently for perovskite is also quite low. I didn't know that, but for amorphous silicon, it is also much lower than it is for crystalline silicon. That's one of the good things about it. It is quite sensitive to large angles, so you don't need to have always direct light. Diffuse light is also quite fine. And it is possible to make it at a low cost. That is not on this slide, but for me that is actually very important. So production costs are really low. So in the older days, these are pictures from the 1980s and 90s, I think. People used to make modules on glass. So this is basically a direct translation from the university work to the production world, because it's the same kind of approach. It works well. There's only one problem, that the costs are quite high. So, and also modules are really heavy. So if you compare this to a crystalline silicon panel, of course they're also heavy, but then you might say, let me take that one that is much more efficient. And that's the reason why many of these companies that you see in this slide, they are no longer working. So what is then a way to use thin film silicon? That is to, I make use of the fact that actually the absorber material is really very thin. So we saw on the previous slide that the whole stack is only a few micrometers compared to crystalline silicon wafers on the order of 150 microns nowadays. So there's really a very big difference, and it means that these devices are intrinsically really thin, and you can bend them. So several companies have tried to commercialize that in a flexible way. Biggest successes were booked by United Solar that you see over here, an American company that went bankrupt about 10 years ago now. And I think all these companies are now gone, except for the one where I'm working. So HyET Solar, they pushed through with with a local investor, they managed to finally convince also investors abroad to actually put some money again here, because now the landscape is very different with investments. Economy is also not the same as 10 years ago. And people are very interested to go for building integrated solutions, for instance, that are very lightweight. And if you can produce your panels near the place where you live, that is also worth something. We've seen with the Corona crisis. If you try to get everything from China, it can also introduce new problems. And people now think this is maybe not so nice. So there is a bigger market now for local production, basically anywhere. And I think in the US and Europe especially, there's already a big market. So efficiency then, I already said a few things about it. How important is this? So of course the parameter is very interesting, and it makes it possible to always say, okay, this cell works better than that one. So in that sense, it is an important parameter. If you have comparable materials, then you can lower your production cost, for instance, expressed in dollars per watt peak or euro per watt peak. With comparable production technology, that's also the case, and then also balance of system cost, the same argument holds. And nowadays, especially, if you look at conventional crystallized silicon installations, more than half of the price actually comes from the balance of system cost, which is basically everything except for the module. So the cabling, inverter, the people that are hired to install the panels, framing and everything. And this is really a factor which is really cheap with flexible lightweight modules, because you can carry them around quite easily. It's easier to place many more modules in the volume of one truck, for instance, and there's quite some benefits over there. So efficiency is in any case a very important driver. Also for the thin film technology, it does need to reach a certain minimum level, but it is much less stressed because balance of system costs are lower, I think. So efficiency is not everything. So back in 2015 already, some agencies said that building integrated PV will become very important. If you want to fill up your whole landscape with panels, you don't want to use agricultural land, for instance, for a lot of panel installations. So it would be nice to make use of already space that is there on the facades of buildings, let's say other kinds of noise barriers next to highways, for instance. You can think of a lot of applications for spaces that are already taken by something where you can easily integrate something that's flexible, whereas crystalline silicon, let's say one size fits all panels are not always the best solution because they're heavy or that they cannot be customized in dimensions. So this really underlines that nowadays there is a demand for lightweight, flexible, customizable modules. So that brings me to the company activities. Yeah, you will probably know, if you have followed the PV developments of the past 10 years, that a lot of things happened in China. That meant also that other technologies were really doing pretty badly. And thin film silicon is one of them. So all these big names, Tokyo Electron, Oerlikon Solar, they all stopped. Different companies in Russia and China that were busy with it, in the Middle East also. Lots of plans were there. The last company that was working on it in those days was Honeji in China, but they changed their mind and they didn't want to have their equipment anymore. And then dark days came, and basically only HyET Solar remained in this topic. And then last year, something actually quite nice happened, which is the reason I can be here today to present this. That's a very large Australian investor with the second richest a person actually in Australia. He wants to basically use his money that he gathered in the fossil fuel industry now to actually push the renewable development all over the world. So this guy is basically buying companies where he thinks there's potential, and they acquired a large stake in the company. And then earlier this year, actually, a large Dutch investment firm, Tesla, they also decided to go for it because of the involvement of Fortescue, this Australian company. So now there's some momentum, and investors they also look at each other, and this made it possible for the company to expand. And now we're going from this 1 megawatt production line capacity to a capacity of 40 megawatts is the first step, then 300 megawatts, and even for Australia, they're talking already about 1 gigawatt. So the plans are really big, and it means they can hire people and expand in all kinds of topics. So where's the company based then? So we have the map of Europe here. If we zoom in on the Netherlands, We see this blue dot on the right-hand side. It's really in the east of the country, close to the German border. And there we have the yellow building where I'm working now. So the company makes flexible, lightweight modules based on thin film silicon, almost all developed using technology and machinery that was developed over the last 25 years. And I will tell you a little bit about how this works. Is there time, or do I need to stop? Okay, so I will take a few more minutes, or what do you think?
Really sort of 1 or 2 more minutes.
Okay.
Yeah, I think.
Yeah. Then, yeah, the manufacturing sequences, that we take aluminum foil, we sputter first the back contact, then we laminate. Wait, no, we put tin oxide on the front, silicon deposition, back contact sputtering, series connection with a lasering process, lamination, which is a gluing process with plastics. Then we remove the aluminum foil from the beginning, and then we encapsulate. So in very short terms, this is the way it is made. Some advantages, I will skip over this because I already said most of it. So what does the product look like? Well, here we have some pictures. So we see a very lightweight product. It's only 600 grams per square meter. It's very thin also. You can imagine you can apply it kind of everywhere because of this. Very flexible in shape. You can even mold it on your roof tiles like this. So it is very aesthetically pleasing. And you can apply it to buildings, so be APV or integrate in a building. And those are the, let's say, the examples of installations, both with really very low cost that you see here. So this is below the installation cost of crystallized silicon PV. Then the progress in the technology. I'm not sure if there's time for this really, but I wanted to show you some results here. So these are, let's say, record efficiencies from the past 10 years. 10% amorphous silicon cell was made, also with people from this institute, I think, at that time. Jacob probably knows it still. Some simulations were done to outline where you can get. So you can reach efficiencies actually above 12%. And indeed, it was demonstrated a little while later that tandem devices could be made, and this is still the record from Delft, 14.8% for a tandem cell. And then for stable efficiencies, because that's also a thing, amorphous silicon degrades when exposed to light, we reached with the community about 12.5%. This is a result from Neuchâtel that you see here. And also, at a very large scale is possible. So this was the last result of Tokyo Electron. They made a module, and the efficiencies reached 12.3%. Then some things that HyET is working on. We have 10.9% now already achieved, not at a very large module level, but let's say a smaller scale module. And want to improve by improving light trapping and silicon layer properties that I will skip for now in view of time. But we want to grow materials with high degree of control. And this is then the last slide. So for the industry, it matters that the efficiencies are high, but also aesthetics, low cost, and reliability are important. It's not just all high efficiency that we need to get. Thin film silicon technology can be competitive when it is basically exploiting its merits. So you can really say that it is flexible and lightweight when you integrate it in buildings also. And several groups and module manufacturers have presented efficiencies that are really above 12%, underlining the realistic potential of this technology. And with that, I would like to thank a whole bunch of people. There's no time to go over them, but this whole team from Eindhoven, where I used to work for years, this crystallized silicon surface passivation team, many master's students, PhDs and postdocs, and the team in Arnhem also, where we make this flexible product. There's also many names there. Now we have about 50 people working there, so I don't have time to name all of them, but they've all contributed in some way. So thank you very much. That was it.
Thank you very much, Jimmy, for this interesting talk with a very nice overview of surface passivation and this nice optimistic outlook. And we wish you, I'm sure we all wish you very best in a competitive world. We have time for 2 very quick questions, only when it is directly, burning questions directly to the talk. We'll continue with more at 5 o'clock.
So I would like to ask a very simple question, that this SiOx layer between the absorber and the contact, it will work, it is working like a kind of resistive layer, because it's silicon dioxide, for example, or any other oxide. So is it not blocking the both kind of carriers, like electron and holes, or is it kind of allowing one kind of carrier? So how is...
Yeah, that's a good question. So the answer is that you need to have a layer that's very thin because it's dielectric. So there's an argument in the community about, is the transport through this layer tunneling, or is it a defect assisted transport? You cannot go beyond, let's say, 2 nanometers if it's a very thin layer. If it's grown in another way, we have some holes in your material, maybe 4 nanometers is initially okay. But it is slightly more electron selective because of differences in band offsets. So it has a slight preference for that. But it can be used in both electron and hole selective contacts.
Thank you very much. One more very quick question. I would like to say that the speakers are also here in the afternoon. So if you've got a lab somewhere here, if you would like them to see something, there is an opportunity, but I'm afraid I'm going to have to drag them away to the what some people think is the most important part of our life, that's the administration. But that's something we don't have any control over, I'm afraid. So thank you very much, Jimmy, again. Now, let me remind you, we will continue discussion, particularly the more general discussion, at 5 o'clock. Okay, we schedule it either before or after Eugene's talk. We can decide on that, but do turn up 5 o'clock. You've got the details on the flyer. I think it's posted downstairs at the entrance. It's what's the number? It's on there. There is, I think, a poster downstairs on the notice board.